All right, 2.5, exponential function and data modeling. Here we go.
Sometimes data from an exponential function does not display proportional growth patterns. This is due to the vertical translation of the function. However, we can add or subtract a constant from the output values y to reveal proportional growth pattern. Then the initial function will also be exponential.
All right, fantastic. I do want you to look at the proportional growth pattern. So if things are proportional, they are multiplying from term to term. And so what we're going to be looking at is we're going to be looking at this vertical translation. And so before we always were in this a times b to the x form, yeah? And we're still there. However, now we're going to add or subtract a constant because it's a vertical translation now. Okay, and so that's where we're going to be working with. So keep going. You're doing great.
Example 1. Selected values from the several exponential functions are given in the table below. For each, find the constant value that can be added or subtracted to the output values to reveal a proportional growth pattern. Then write an equation to model the function.
All right, fantastic. All right, and so here we go. So let's look at our input values of 0, 1, 2, 3, 4, blah, blah, blah. And so these are all the same inputs, widths, and so we don't need to worry about them. So let's do what we always do. 7 to 13 is what? 6. And then 12. And then 48. So it's not linear. It's not going to probably be quadratic. And so we're not adding things. And so what's happening to it, though? 6, 12, 24, 48. What's happening to it? Okay, they're being multiplied by what? 2. All right. And so anyway, so our differences are being multiplied by 2. And that gives me my b to the x. And so it's going to be 2 to the power of x. So it's exponential because it's a proportional growth. But I need to actually find this a, and I need to find this c. And so what we're going to do is we're actually going to find a system of equations here. All right. And so anyway, a lot of the times I kind of guessed and checked back in the day. However, let's come up with a better system of it. And so anyway, we're going to find a system of equations. So we're going to look at like these first two columns and rows. All right. And so the first ordered pair is 0, 7. And so if I were to substitute in 0 right here, 2 to the power of 0 is what? 1. Is everybody following me? And so I'm left with this a plus c is equal to 7. Because when I substitute in 0, I'm going to get 7. But I don't know what my a and c are. Is everybody following this? Okay, this is vitally important. And then I'm going to substitute in this 1 and this 13 now. And so when I substitute in 1, 2 to the power of 1 is what? 2. And so now I have 2a plus c, which is equal to what? 13. So now I have a system of equations. I have 2 equations, 2 unknowns. And now we just solve. All right. And so what I personally would do is I would like distribute the negative right here. I'd go pew, pew. And so that would cancel out my what? My c's. All right. And so now when I add straight down, how many a's am I left with? Just 1 a. And what is my constants do? It goes to 6. Because my c's canceled with my system of equations. So if a is equal to 6, what does c equal? 1. And so now I'm basically solved for my equation. And so now I end up having f of x is equal to 6 times 2 to the power of x plus 1. And so there's my exponential function that got shifted vertically. All right. So again, we look at our input values. So they're the samesies. So now let's look at our output values. So how do I get from 2 to 10? 8. And then 24. And then 72. And then 216. Well, what's happening between them? It's being multiplied by 3. So my proportional growth here is multiplying by 3. All right. And so this gives me my g of x. I don't know my a yet, but my b is going to be what? 3. So now I have 3 to the power of x plus my constant. And I need to solve for my A and my C. All right? And so now I personally would look at these numbers right here so I don't have to work with too big of numbers. Make sense? All right, it doesn't really matter which two you pick. It really doesn't. However, I would pick those so I don't have to work with so large of numbers. So when I substitute in 0, I'd end up with what? When I substitute in 0, what happens is my 3 to the power of 0 comes to 1. So I'd end up with A plus C is equal to 2. All right. Now I'm going to substitute in my ordered pair of 1, 10. And so when I substitute in 1, I'd now have 3 to the power of 1 times A, which is 3A, and then plus C, which I don't know, which is equal to what? 10. All right. And so this is where I would distribute the negative and then add. So I go boom, boom, boom. And so then when I add straight down, how many A's do I have? 2. That's more than some of you. And then I'd have 2A, which is equal to what? 8, because my C's cancel. All right. And so then what does A equal? 4. So A is equal to 4. And so if A is equal to 4, then what does C equal? Negative 2. And so then my G of X would equal what? 4 times 3 to the power of X and then minus 2. All right. And so there's how we can get that exponential function. All right. All right. Let's do it again. All right. So again, I look at my input values. They're equal widths. And so then let's work with my H of X. So how do I get from 63 to 31? Negative 32. Then what? Negative 16. Then what? Negative 8. Then what? So what's happening between those gaps? Okay, I don't want to call it divide by 2. What do I want to call it? Times 1/2. All right. And so now what's my B? 1/2. So now I end up having H of X. I don't know my A yet. And then I have 1/2 to the power of X plus C. Right? Pretty good so far. Okay. So now I'm going to look at my ordered pairs. So when I substitute in 0, what happens? I'm just left with what? 1. So now I have 1A plus C, which is equal to what? 63. All right, now this is where it gets slightly tricky. So now I'm going to substitute in 1 comma 31. And so now if I substitute in 1 comma 31, this is now a what? How many A's do I have now? 1/2. All right, so now I have 1/2 A and then plus C, which is equal to 31. Again, how can we get rid of our C's? Distribute the negative and then add straight down or subtract them. Okay, I like to distribute the negative and add. And so then how many A's do I have left? 1/2 A is equal to what? 32. And so A would equal 64. And so then once A is equal to 64, what does C equal? Negative 1. And so now H of X would equal 64 times 1/2 to the power of X minus 1.
Modeling exponential functions from data. An exponential model can be constructed if we are given either the common ratio and the initial value or two input-output pairs. We can find the initial value and the base common ratio of these two pairs. Example 2, for t being in between 0 and 30 minutes, the number of fans inside a large sports stadium can be modeled by the exponential function f of t equals a times b to the power of t, where f represents the number of fans inside the stadium t minutes after the doors open. There are 47 people in the stadium 2 minutes after the doors open, and there are 2,602 fans inside the stadium 20 minutes after the doors open. Use the given data to write two equations that can be used to find the values for constants A and B in the expression for f of t.
All right, fantastic. So I like to think of these as ordered pairs. However, this one's saying write an equation, so we're going to do it. So what's my input value of this? 47 people after 2 minutes. So what's my input value?
Mr. Flagg?
And so we're going to find f of 2, which is equal to a times b to the second, which is equal to my output of 47. And then my other equation would be f of 20, which is equal to a times b to the 20th power, which is equal to this 2602. All right, and so from there, we're actually going to create the regression model. All right, and so let's go back into our calculator, and we're going to press Stat, and then we're going to go to Edit, clear out whatever you have in there. This is where I'm going to pause my video. All right, and so now we have that as our exponential regression model. Okay, let's do example 3 now. Noah, pick somebody.
Lucas.
Alright. Example 3. Selected values of the exponential function g are shown in the table above, where g of x equals ab to the power of x. Use the given data to write two equations that can be used to find the values for constants a and b, and the expression for g of x. Find the values of a and b.
All right, so we're going to do exactly what we just did. All right, and so let's find our equations first, just in case they ask that. And so we're going to find f, or sorry, not f, but g. So we're going to find g of 3, which is equal to a times b to the third, which is equal to this 21.54. And then we're going to find g of 8, which is equal to a times b to the what power? 8th power, which is equal to this 3.62. All right, and then we're going to go to Stat and Edit. So after we put it in our list, then we go to Stat, Calc, Exponential Regression, and we can find our A and B that way. Awesome. All right, so now we're going to go to natural base E, developed by Leonard Euler, or discovered, I should say. All right, and Campbell's going to read about our natural base E because she likes Leonard Euler. All right.
The natural number e is often used as the base in exponential functions that model a contextual scenario.
All right, so E is very important. It's an irrational number, just like pi. It keeps on going forever and ever. If you wanted some more digits, it'd be 2, 8, 1, 8, and it keeps on going without a pattern anymore. All right, here we go. Example 4.
The number of bacteria in a particular culture can multiply the exponential function b of t is 17b to the power of 0.31 t, where t is measured in hours. Let a of t be a times b to the power of t, be an equivalent expression for b of t, find the value of b.
All right, fantastic. All right, and we're going to find A. All right, so if this is equivalent, what would be my A? Please don't overthink this. What's my A? If they're equivalent, what's my A? Somebody said it? 17. All right, that's it, just 17. And then what's my B?
2.718.
Okay, if we needed to actually, so it would be that to the power of 0.32. And so my B is just E to the 0.31. All right, and so that's my base. All right, because that's what's given to us there. All right, part B now. Part B.
Find the average rate of change of b of t over the interval t equals 1 and t equals 7.
All right, perfect. So what is an average rate of change? We're going back to our second lesson of the year. What is an average rate of change? Algebra slope. All right, and so all we're doing is finding b of 7 minus b of 1 over 7 minus 1. All we're doing is finding algebra slope. All right, and so we need to look at our calculator now. All right, so we're just going to make our fraction. All right, so I do that as alpha y equals. All right, so then we found our average rate of change by putting that into our handy dandy calculator. All right, part C.
Find the number of bacteria b predicted by the model after 15 hours.
All right, so on this one, all we're having to do is do what? Substitute in what? 15. So we're finding B of 15. And so we're substituting in 15 right in there. Elizabeth, what'd you get? 48. Love it. All right. All right, Kefa, go.
Example 5. After 50 deer were introduced to a large wooded area, the population of deer in the wooded area can be modeled by the exponential function v of t equals a times b to the power of t, where t represents the number of years since deer were first introduced to the wooded area. The population of deer increases by 30% each year.
All right, so it increases by 13% each year. So let's find A and B for our expression of deer. So what is my initial value of deer here? What is my A? 50. All right, so I got 50 there. And then it increases, the deer increase by 13% each year. So what is my B?
0.13.
It's not 0.13. Why isn't it 0.13? Do you remember when B was in between 0 and 1, what happened? It was actually a decay because it actually goes down. Because if you multiply by something in between 0 and 1, what is it? It's actually less than what you started with. Remember me doing the fraction of like 1/2 times 1/2? What's 1/2 times 1/2? 1/4. It actually decayed. And so if it's an increase of 13%, then my actual B is really what? 1.13. All right, because it's 100% plus that 13%. All right, and then it's to the power of t. Now I know this one didn't ask it, but I want to talk about it. What if the population of deer decreased by 13%? Then what would be B? 0.87. Exactly. All right, because we're taking 13% off of the 100% now. All right, very good. All right, part B now.
According to the model found in part A, what is the population of deer in the large wooded area after 6 years?
All right, so what are we trying to find? D of 6. All right, so we're just going to substitute in 6 right there. So we ended up with 104.0976 deer after 6 years. And some people ask, how in the world can you have a decimal of a deer? Pregnant. All right, part C. Part C.
Find an equivalent expression for d of t where t is measured in months instead of years.
All right, so we need an equivalent expression with this one, but instead of years, we now want months. How many months are there in a year? 12, good. And so d of t would equal 50 times 1.13 to the power of what? Is it 12t? Or is it t over 12? It's t over 12, exactly. It's not 12t because then they wouldn't be equivalent. And if you think about it, if you substitute in 12 months, you'd have a power of 1. And if you substitute it in 1 year, it'd be the same. All right. If you were to do it backwards, it'd be like 144 to 1, and that would be very different. All right. All right. I want to do one more. And so part D, we're going to find the time. The population of deer reaches, let's say, 100. All right, so we're going to find the time the population reaches 100. And so what are we trying to solve for? T or D of t? We're trying to solve for t in this case, and I'm giving you what? 100. I'm solving for d of, like I'm giving you d of t. And so what we're going to do is we're going to set 50 times 1.13 to the power of t equal to 100. Now, as this chapter moves on, we're going to find other algebraic methods to solve for t, but I want to use your graphing calculator right here. All right, so let's go back to y equals. All right, so now I find my intersection of my graphs after I use zoom fit, and I end up getting time is equal to 5.6714 years. All right, was when my deer population will reach 100. All right.